We have more than 150 attendants to this course, and that is much more than we have thought originally. That number shows the interest of the international port and waterways community to have lectures on these important subjects. I hope that you have been able to download and to read the excellent and recently published book from Professor van Koningsveld and his team. The possibility to attending this course is very remarkable, and I wish you all a very fruitful week. Thank you. Pablo.
Thank you, Raúl. I think now we are ready to keep moving ahead. Just to provide a small introduction, but then the floor is yours, Mark. Today we have Mark van Koningsveld, the lead professor of Ports and Waterways from the Delft University of Technology. And well, I think no further introduction is needed from my side. Mark, the floor is yours, please.
Did you want to say something about handling questions?
Yeah, that's a very good point. And thank you for reminding, because of that you are the professor. Well, just basically we are going to structure the course in 2 blocks. There will be a first block where Mark is going to give a general overview of the vision of TU Delft on ports and waterways. And all questions, first, please write it on the chat. For those following on YouTube, also you can write it over there. Questions will be handled at the end of the session. And there will be moderators either in this session, that's me, and on the YouTube meeting room is Sebastián Iglesias. Therefore, all the questions will be addressed by us. For those within the Zoom meeting, well, we will be calling by name, and you can have the advantage to ask the question directly to Mark van Koningsveld. So I think with this, we covered everything. We will have a break in between for a coffee, and that's, well, all the logistic parts.
Okay, excellent. So shall I try and share my screen? See if that will work. Should be. Okay. All right. Can you see everything on the screen now?
Yes.
Okay, excellent. Well, I unfortunately don't see any faces anymore, so I'll try to keep track of what is going on. But I think ideally the way we discussed it, if we can collect the questions at the end, and then we'll have, let's say, a more interactive session at the end. Well, as I was introduced by Pablo, my name is Mark van Koningsveld, and I am currently the professor of Ports and Waterways at TU Delft. And I thought maybe first I start with a very brief introduction of myself so that you know who it is that is talking to you. I like to introduce myself basically by 3 components that always come back in my work experience. So first of all, one of the main things that I have always defined my career is that I'm trying to do research and science in support of decision-making in practice. And this has been actually the topic of my own PhD work already, unfortunately, several years ago, but that has always stuck in my daily practice. And then while I'm addressing, obviously, at the moment, mostly ports and waterway related problems, there are 2 sort of running components that seem to always come back. And one is, let's say, a sustainability part. So I was heavily involved in the Netherlands in the Building with Nature program, where we look at promoting nature development around infrastructure projects. And also I have been quite active in looking for introduction of digitalization into data science type problems. So to go back once more, so my own PhD was on this topic, and there I developed, let's say, a schematic way to match clearly defined problems with quantifiable quantities that you can actually either quantify with using data or with a simulation. And I'm hoping at the end of this lecture, you will find that I still use this in my daily practice a lot. And if you look at building with nature, maybe you've seen some of these publications. So we've worked on a method development on how to integrate natural aspects into infrastructure development. But I've also been applying that myself in the sense that I have worked on developing my own coral breeding laboratory, which may seem like a bit of an odd sidestep. And we've also worked on, let's say, underwater microphones to keep marine fauna away from construction projects. And when it comes to more the digitization part, I've worked on methods to actually introduce working with data models and tools into the field of civil engineering, and mainly also inspired by lots of field work that I did also myself. And I was very happy to be awarded a National Science Award for that already a few years back. With that, I've really integrated also into my own group here at TU Delft. And recently I've been participating in two large pieces of literature. So one is, perhaps you've seen it pass by, this book by SEDA and IADC on dredging for sustainable infrastructure. So those are methods for infrastructure development focused on sustainability. And very recently, our own book for ports and waterways, which was already announced in the beginning, that is now available as an open textbook. So, well, if you look at my background, so then you can always expect, if you see me, to be addressing practical decision problems with scientific information, ideally also with a sustainability component and a data science component. So, well, now you know a little bit about my background. And today, what's also quite important is that I am in part-time employed by TU Delft as a professor ports and waterways, as already mentioned, but I'm also still innovation manager at a dredging company, Van Oort. And there I'm also busy with all sorts of supply chains over water. So those two different roles are quite well aligned and maybe only differing in scale. Okay, so for today, I had the idea after this 5-minute introduction to spend, let's say, maybe the first block. I said here hour, I'm not entirely sure it will be exactly an hour, but we'll try to time it so that I will introduce you in the first block about what TU Delft is doing on the topic of ports and waterways. So what are some key aspects that we've integrated in our teaching? And I'll try to illustrate that on some master theses that we have completed in the past year. And then after a brief coffee break, then I thought the second block could be maybe taking you along a few of our research topics. So I thought I would illustrate some of the things we do by highlighting 3 different PhD studies that are currently ongoing in our group. And then you will get to know our group a little bit, and hopefully, let's say, by discussing also these types of research, maybe you'll also learn a little bit about how you can actually approach the topics that we have been addressing in these PhD topics. And then at the end, I'm hoping to give a little bit of a pointer towards the next 2 lectures, one by Alex Kiricek tomorrow and one by Fedor Baart the day after tomorrow. But let's start with the first block. So the way we actually address at ports and waterways the topic of creating focus in our group, it stems to a large part from this particular picture. So here you see this overview that's being released by UNCTAD every year, the review of maritime transport, and here it shows, let's say, over the years, let's say the total amount of cargo that has been shipped internationally over the years, and you see that it's steadily growing up to about 11 billion tons at the moment. And here you see basically the same figures, but then in terms of growth. So you see these are the most recent figures actually, and then you see that containers, main bulk, other cargo, and tanker trade, they are almost equal in size with maybe container trade, the smaller one, but it's rapidly growing and gaining ground. And so you see that massive amounts of cargo are being shipped over the world, and almost 90% of that, or as like a rough estimate, of course, is at least carried via international shipping. So basically everything we touch and see during the day has a high potential of being shipped at some point from an overseas location when it's imported. So when it comes to, let's say, maybe our digital equipment, our clothes, sometimes our food, our car, you name it, everything has a high potential of being shipped from an overseas location. So if you look at these cargo flows, then yeah, basically it always works in a way that you have, let's say, somewhere a production location. So let's say, let's call it A. Goods are shipped from A to B. So let's say there's a production location near A, and maybe the end customer is at B. And then let's say that all cargo goes through a number of steps. So it will be produced somewhere, maybe from there be transported to an inland port, for example, where it is maybe shipped with inland transport to a seaport. There it might be, let's say, unloaded and loaded onto a seagoing vessel, and then maybe be shipped for literally tens of thousands of kilometers to an import terminal where it's unloaded, stored again, maybe loaded again on inland ships, and moved towards the end customer. And so this massive amount of trade that is moving around the world follows basically always a supply chain more or less like this. And actually this supply chain is not running in free air, but it's actually based on a solid foundation of infrastructure. So here you see the same type of supply chain again, but then from a factory towards either by road to a seaport or via inland water transport. Then you have the seaport with the long distance shipping, and the same at the end location from the seaport to the end user location somewhere inland. Well, if we look at one half of this supply chain and we project to it not sideways but more on top, then it could look something like this maybe. For some reason I have this bar here in front. I'm hoping you don't see that as well, but okay, let's continue. So here you see the same end stretch of an international supply chain where maybe from some overseas location A, the cargoes need to go to, let's say, some city near location B, and then you can understand that large seagoing vessels, they approach maybe a seaport and then offload their cargo, and it goes either via pipeline, rail, road, or inland shipping towards this hinterland location where it's then in the end ends up with the end user. And of course, let's say the large transport stretches overseas, they are very important, but also they cannot really be influenced that much, right? So it's the large vessels that are just creating this line trade between an export port and an import port, but the biggest difficulties are actually occurring when you are moving more inland. So then suddenly you will find that, let's say, maybe water depth, the presence of limited water depth, or the presence of locks and bridges and things like that, they will affect the efficiency of these supply chains very much. And that is basically what our research is going to focus on. So we look at these kind of systems basically at different scales. So we could look at the system as a whole, but then to really understand how that system as a whole works, you really need to understand of its individual components. Or sometimes we might be asked to design an individual component, like for example, a new lock or a new terminal, but then basically you can only effectively design that if you are aware of the larger system in which it fits. It doesn't make any sense to have a high capacity lock if the rest of the network is not capable to handle that kind of traffic. So different scales are important, but not just spatial scales, but also temporal scales are important. So we look at the long term, where long term is so long that you can actually influence the system. So you might be able to dredge a new channel or create a new terminal or actually invest in a different fleet And this is all possible, but it takes a lot of time to actually complete. And we can look at short-term problems, and then short-term is defined as so short that you cannot modify the infrastructure or the fleet composition. You just have to make the best of it with what you have. So that typically means adaptation to new circumstances or traffic management interventions or so to handle new situations. Well, then next to, let's say, the large scale and the smaller scale, the long term and the short term, it's also quite important that any port and waterways problems always have multiple stakeholders involved. So it's very important to find an optimal balance between the need of those stakeholders. So you can imagine that maybe what is important from a terminal operator's perspective might be very inconvenient when it comes to, let's say, a shipping captain's perspective or so. And so to really understand what is the best solution for the system as a whole, you have to be able to show the effects of different interventions to different stakeholders so that you can come to an agreed end conclusion. And then these systems, you might say, okay, once you've got this designed, then there's nothing more to it, but these systems are always under development. And so you see that in the past decades, we've seen big developments of increasing vessel sizes. Typically in the container transport, we've seen massive size increases. We see also developments in trade where new trade blocks are up and coming, or maybe other trade routes start to emerge. Things like climate change, they start to affect these port and waterway systems. You see also an increased focus on sustainability. Some of that is related indeed to climate change and emissions, but you can also have a focus on sustainability when it comes to natural habitats and so on. You see there, at least in Europe, it's becoming very prominent that you see the effects of the energy transition. So people are looking for active investments in reducing energy consumption and footprints, and also looking at different types of fuel and figuring out how that affects the whole system. Things like digitalization, so the use of data and communication tools is increasing. And you see things like autonomous vessels that start to play a role. And basically all these things make that any port and waterway system is actually always somehow moving towards a new situation. And this is also explains, let's say, the title of this presentation and also the title of our book. So we called it Ports and Waterways, and then with the subtitle as Navigating the Changing World. So basically how to anticipate and actually invest in being ready for the future. That's seemingly a never-ending process. Well, this is not just the way we look at ports and waterways systems in our group. What you see here is a picture provided by the Port of Rotterdam, what they use internally. So unfortunately, the words are in Dutch, but I think you can, if I translate it a bit, you can easily understand what it says. So here, Port of Rotterdam highlights a number of challenges that they are facing. So they are facing issues related to water quality, increasing vessels that need to still fit into the water infrastructure. They also have to deal with the energy transition. So what to do with old forms of energy and how to accommodate space for new forms of energy. They deal with aging assets, so when to replace and what to replace it with. They deal with increasing pressure from surrounding population, and that also provide demands for the quality of port performance. There are issues related to mobility, electrification, etc. And so you see that all those things that I mentioned, they quite resonate with the picture that a port like Port of Rotterdam also announces themselves. And then if you take another view at the same thing, and then you see that next to all those development, there's like a supporting infrastructure that very much relates to data and algorithms for analysis. So this picture typically shows that to make these changes and to understand how the ports work, you need data on water depth, on hydro, meteo information, but you also need data on infrastructure forces, like this is boulder pull forces or a deformation of quay walls, the availability of berths, for example, or the availability of barges. All these things, they are very much supported by these days by data and modeling systems. So it all hopefully underlines the story that I was just telling. So if we look at ports and waterways, so what do we regard as ports and waterways issues? Well, we say, okay, we look at the design of port and waterway systems as where ports and waterway systems for us are, let's say, water infrastructure systems that support supply chains over water. And we believe that these systems, that they are quite complex to manage because, let's say, if you change something at one location, it might affect, let's say, sometimes supply chains several tens or 100 kilometers further in the network. So there's a very complex interaction of things ongoing. And to understand this, that requires simulation, but also economic evaluation. And so it's not just thinking of one way to improve the way that the system works. There are numerous alternatives for improvement. And what you probably want to do is to understand the cost of certain alternatives, but also explain the benefits. And here again comes this link to older stakeholders into play. And what is also quite important is many of these feedbacks that can cascade through a system, they are typically non-linear, and that makes it also very hard to sort of rely on intuition and guess what is going to happen. You really need to investigate to not be surprised. Well, then in that complex problem field, we as Ports and Waterways at TU Delft like to focus, as I mentioned, on water infrastructure design. But to really be able to do that, you need to basically know about a few other disciplines. So you need to know about nautical traffic, so the movement of vessels, how do they move over the network? But you also need to understand about logistical processes, so how many vessel movements are needed to get certain amounts of cargo from A to B, but also if the demand for a certain type of cargo increases, how many more vessel movements can you expect? But also you want to know about environmental and physical restrictions, basically, on your supply chain. So these can be natural, like available water depth is a typical natural restriction to the performance of a supply chain. But there can also be man-made restrictions, like traffic management rules or environmental restrictions, and they might also affect the performance of the supply chain. And then typically, we realize that to understand how these port and waterway systems work, we need to actually include typically engineering knowledge from different fields. So it's not just enough to look at it from a civil engineering perspective or a hydraulic engineering perspective. But typically, we also need to involve knowledge from, for example, the shipbuilding department to understand about energy use, or about the production of sound or fine sediment spill or forces that are exerted on either a vessel or on quay wall infrastructure. So it's quite an integral field. The way we try to train our ports and waterway engineers is that they are aware of this, so that they understand that it's quite an integral, multifaceted problem, and that they should try to quantify as much as possible what is happening in this system, and also be able to discuss and present it to different stakeholders so that you can come to a mutual agreement on what is the best way forward. So this is the way we try to view our field. And it's clear that we rely heavily for this on data and simulations to be able to quantify. So that brings me to, let me see. Now it's moving up. So that brings me to a next part of our education program, is that we said, okay, it's so important for ports and waterways engineer to understand, let's say, that ports and waterways and all the things that are happening on it, that they are part of an integrated system, that we thought, okay, if we look back to our education material, before, a few years back, we had separate books and separate lecture notes for different elements. So we had a separate a book for ports and terminals. So we had separate lecture notes for waterways. We had separate lecture notes for environmental effects, separate lecture notes for system performance. So we thought, okay, it would be so much better if we could somehow integrate it into one publication that just discusses all these things in a well-balanced way. And well, that's what we spent our past, about 2 years of our time. We spent a lot of effort to try and work out a book of that kind. And it is, as was mentioned by Pablo, has been recently published via Delft open textbook. So I think you already received the link earlier, but you can just go there to this link and download this book, and everything that is in it has been published under quite open licenses. So it's free for reuse as long as you attribute, let's say, the original authors and don't use it for commercial purposes. Then it's basically free for you to use also in education programs and other things. And if you would open this book, then one of the first pages of the book, it sort of highlights the principle of writing for this book. And there we say, okay, we look at ports and waterways at the book to enable students to compare alternative strategies for the design and operation of waterborne supply chains. And that has a few elements. So, of course, we want students to be able to specify the important aspects of port and waterway systems at different scales, as I just introduced. But we also want students to be able to perform performance analyses of these networks. And then performance, we mean performance with respect to a given objective. And that could be capacity, efficiency, safety, and sustainability. Well, there are, of course, probably many other objectives, but these are the 4 that we've highlighted throughout the book. Well, then if you see an issue with your performance, you might want to modify your system. So the next step is to figure out how to come up with new functional designs that hopefully are an improvement of your system. And then we focus typically on, let's say, functional design. So in terms of the number of elements, the order of magnitude dimensions, rather than really the construction engineering drawings, if you will. So we look at functional designs for the moment. And then we think it's also important that if you have different alternatives that you have thought of, that you also can perform feasibility studies where you can basically do cash flow analyses and get some first order cost estimates to understand, okay, what is the investment associated with this improvement and what is the likely benefits. So, well, anyway, all of this we have tried to incorporate in our book, and we're keen to learn from you guys if you could actually get it out of the book. So if you have tips or ideas, and we'll be keen to hear it. Next to, let's say, that we think that ports and waterways should be treated as a coherent system, we also noticed that to actually quantify these complex systems, we need a different type of engineer than we saw before. And that's sort of part of a larger trend, in the sense that almost in any field of engineering, you see that software and data are becoming more and more fundamental to research, consultancy, and engineering. And so any design, any study typically already starts to make use of large heaps of data and all sorts of algorithms. So it's important for young professionals to also become skilled in, basically almost become software and data engineers, but then with a technical background. And this type of role that has been, it has been coined by Microsoft under the term research software engineer, has a bit of a background in the medical profession. And there you see, let's say that research software engineers, they sort of combine both an intricate understanding of the research, so that technically they know what they're talking about, so they understand the substance of their field of expertise, but also they have the capabilities to harness that knowledge into programming and software, so that you can actually, analyze a whole bunch of alternatives rather than maybe just 1 or 2. Actually, this particular skill, that's what we need also for ports and waterways. So it's not just the medical profession or other data-rich environments, but also ports and waterways. They typically require this skill, and often of different disciplines also. So we've tried to include this kind of education also actively as part of our curriculum to help students to develop the hard skills related to that. And for that, we set up what we call the Ports and Waterways Coding Lab, and it's typically focused at students doing their master thesis. So they spend typically 8 or 9 months on a given topic, and then we try to surround them with other students, but also with professionals from various organizations from practice to help them learn how, what kind of tools are available, how to best use large data sets and so on, so that they really start to experience how to address these kind of topics. And actually, we've done it in such a way that from student to student, we try to really also instill them with the FAIR principles. So those are, let's say, the open science principles that data and tools should be findable, accessible, interoperable, and reusable. But that doesn't mean only that if you make something, you leave it for the next person to be reused, but you also actively should try and reuse what is available already yourself. So this line of thinking, that's what we try to do in this Ports and Waterways Coding Lab. And as a result, we have a bunch of development lines that typically have numerous master theses, built on top of the work by predecessors, so that we gradually develop toolboxes that can be used for a whole range of things. So in the coming few slides until the coffee break, I'm trying to highlight a couple of these theses that are presented, and maybe treat one of those in a little bit more detail to hopefully illustrate how we look at defining alternatives and quantifying them, and what kind of comparison we want to enable. And actually, our tools, when they are published, they are openly available via our TU Delft CITG GitHub channel. So you can find, let's say, this software over there. For now, it's maybe a bit too far to really show you how to download it, but it's available for your use. So just as an example, one of our tools is it's called Open TISIM. So it focuses on terminal investment. And here we actually want to see if we can somehow make a parametric link between changes in demand and terminal infrastructure, and how that translates to overall cash flow and net present value. So basically, we regard, just as I highlighted before, we take a certain supply chain into account. So in this case, the topic was agri-bulk type of cargo, where you have vessels that need to transport a certain amount of cargo. And then you can figure out, using all sorts of PIAN guidelines, how many quay walls you need, how much unloading equipment is required, and also how to transport from the quay to the storage facility, and from the storage facility to hinterland connections, etc. So basically, to figure out what the total of such a supply chain over the terminal looks like, there's a bunch of guidelines available. And then we want to figure out how those investments, of course, start at the T0, but then also how they can be influenced over time. So you get basically a certain terminal at T0, and then if demand increases, there comes a point when certain triggers maybe require you to construct a new quay wall with a new unloading equipment, or increased storage facilities, or increase the hinterland connections, and so on. So all these investments further down the line, they influence the cost profile of such a terminal. And therefore we try to automatically derive, by using all sorts of experience numbers, what the cash flow overview is of these kind of investments, where the large red bars represent the so-called CAPEX, so the large-scale capital expenditures for new terminal, new quay walls, new berths, new cranes, and the dark blue lines, they are more focused on the operational expenses. And at the other end of the spectrum, of course, you have the revenues. So hopefully by having these investments in place, your revenues might also increase. And then if you calculate back what the present value of all those cash flows is, you can get an idea of whether or not this terminal is profitable for a certain demand scenario. And the nice part of integrating this into such a package is that if you can do one calculation, and then you can do 100 of calculations, if you will, for example, varying thresholds of service levels, for example. And then this way you can explore how different scenarios might lead to different business cases. Well, this is one tool that we have. Another one is related to, we call it open CLSIM, that's related to complex logistics. So in this case, we have cargo that needs to go from A to B that governs how many vessel movements are actually going back and forth. And this has been applied, among others, on issues related to low water levels on our main rivers. So if you look at the port of Rotterdam, it serves typically a large hinterland with Duisburg as one of our main back ends in the hinterland, but actually further down all the way to Basel, there's let's say cargo is being transported. And one of the things that was happening in 2018 was that there was very little rain and actually water levels dropped dramatically. And as a result, we get news items like this. So it's in Dutch, so I'll translate. And we got some news items saying that, okay, the water levels are low and now more and more vessels are needed. So this is typical interaction between the state of the river and how the supply chain needs to operate. So if you look at data that was actually collected, the light green part, and then you could see that during the dry period, which was this part of the year, you see that the number of trips would drastically increase because the vessels could load lesser cargo to avoid running aground in the shallow waters. Well, but because they had less cargo, they needed more trips. But even though they had more trips with less cargo, in the end, they ran into the maximum transport capacity, and then you saw that there was a drop-off in the total cargo that could be moved. For that purpose, we developed a digital twin to analyze inland water transport corridors. And later this week, Fedor Baart will hopefully introduce you into this particular digital twin in a bit more detail. But I will just show you some of the things that we looked for in that. And so we looked at this Rotterdam Basel route for a given shipping company, and then wanted to figure out how many vessel movements were needed to move a certain amount of cargo from A to B. And then you can basically, with OpenCLSIM, you can run a planning like here. And so you see that there is a number of vessels that perform a number of activities. So they need to go to, let's say, the port to actually be loaded up. And so all these are loading actions, and then they are sailing full towards the destination. They are unloaded again, and then they need to sail back and then load it again, and so on. So if you know a certain amount of cargo needs to be transported and you know which fleet is going to be responsible for it, you can calculate how much time it would take roughly to do this. So in this case, this is like the project duration notation, and under normal circumstances with 6 vessels, and it would take 13 days and 1 hour to actually complete this activity. But then if you would have less water going down the river, so Lobit is here, this entry point in the Netherlands, and if there's less discharge, then the water levels on the river will be lower. And if you have a lesser discharge, then you see that cargo, the vessels cannot load as much cargo as before, so they need a few more trips here at the end. And as a result, the project becomes almost a day and a half longer. If you would further reduce the discharge, even less cargo can be taken on board, and the project needs even more vessel movements, and the project will take even more time. So if you do that, let's say for a whole bunch of discharges, you can investigate how with declining discharges, let's say the time it needs to transport 30,000 tons of cargo, it sort of escalates. So this is typical non-linear relationship, so that as the water level in the river drops, the performance of this supply chain increasingly deteriorates. And that's what you want to understand to be able to advise to either shipping companies or port operators how they should adapt their activities. Well, a similar type of tool is called OpenTISIM. That's focusing on transport network performance, and where OpenCLSIM really is driven by a cargo transport demand, and OpenTISIM is much more driven by actual origins and destinations that are provided by the user. And then you can let vessels move over a certain transport network. And then as they move, you can calculate interesting things. So in this case, we had a student who was looking at trying to estimate emissions or energy consumption and emissions from moving vessels. And by that, we integrated knowledge on resistance calculations from vessels, which were based on ship dimensions, but also the sailing speed and fairway properties. And then you could calculate resistance. And if you know what resistance you need to overcome for a certain speed, you can estimate how much power is needed to do that. And if you know for how much time you need that power, then you can estimate the total energy. And if you know the total energy requirement of a trip, you can use things like engine age and the partial engine load and emission factors to translate this energy consumption to fuel consumption and actual emissions. And we applied that to start with on AIS data. So AIS data is, let's say, automatic loggings of large cargo vessels to log their position. So you will know their position in space and time. And from that, you can derive things like speed. And then if you have that information and you know something about the vessel dimensions and the waterway properties, you can perform these calculations and come up with these emission maps. And if you have these emission maps for the AIS data, which is, let's say, an actual situation, you can also implement it in this tool to actually test, let's say, different policies. So one of the tests that was done was to see, okay, if we have a certain fleet operating on these waterways, what if we, for example, replace all engines that are older than 2007 with new engines? And that, of course, requires an investment, but what could be the emission gain? And so those are the things that we try to analyze and quantify, and then you get these kind of numbers back. After the coffee break, I will go into this particular topic in a little bit more detail. Well, where we had the previous tools that I described was related to terminal development and vessels movement on the network. A very modern and interesting topic nowadays is, of course, in light of the energy transition, what if we wanted to import, for example, large amounts of hydrogen to a port? And then how could you analyze the performance of such a supply chain? And then what is interesting about hydrogen, for example, is that it's transported in different forms. So there are different carrier types that you can transport hydrogen. So you can either transport it in a liquefied form, if it's really cold, or in a gaseous form, or sometimes attached to a certain carrier. But whichever way of transport you choose, it will have effect on the way your total supply chain looks like. Because if you have hydrogen in a certain form, well, maybe you need to include reconversion plants at some locations. Well, in this particular study, we tried to figure out how, let's say, the configuration of these supply chains, and then including, let's say, things like the demand. So you see that if the demand increases, you get economies of scale, and how distance would affect which is the best option. And by that, we combined. So if we looked at these supply chains from an export terminal to an import terminal to an end user, basically we applied OpenTISIM on the terminal location and then OpenCLSIM for the transport. and for the terminal again, for the transport, and for the terminal again. And this way we could actually quantify how different designs and configurations would translate to cost per ton of hydrogen. And you could actually map out, let's say, different locations and distances and compare different supply chains. So that is, I think, an interesting overview of some of the tools that we've developed to actually look at these waterborne supply chains and to move towards a conclusion. Let's say, just for this first hour, I thought I would discuss in brief, let's say, how we applied this kind of analyzing to analyze, let's say, the emission performance of different dredging projects. So if you regard a dredging project as a miniature supply chain, so it's also moving sediment from A to B with vessels over a certain route, and it's quite comparable to moving containers over a much longer distance, but for now it's a little bit simpler in scope. So to explain to you how we would analyze such supply chains, I would like to take the case of Dutch coastal maintenance, to safeguard our low-lying country from rising sea levels and storms. Basically, every year we apply 12 million cubic meters of sand to the Dutch beaches. And this is done by dredging operations, and it can be done either, so it can be applied near the coast either by a process called rainbowing, where you jet the water sand mixture over several tens of meters, or it could be by bottom door dumping. I didn't include a picture of it because it wouldn't show very well in a picture. Or you could actually, of course, pump the material via a nearshore pipeline to the coast, where then the material had to be reprofiled by land-based equipment into the proper profile. And one of the questions that came about in the Netherlands, also in light of the Paris Climate Agreement, was what is actually the energy consumption pattern and the footprint of these projects, and what is actually possible in reducing these footprints. So that's what this student was focused on. And basically, the way we did that was we again simulated we decomposed a dredging operation into a series of what you can call discrete events. So separated events that you can estimate the time of. And then, if you do that, then let's say these tools that we've developed, they allow you to do a basic agent-based simulation. So if you look at a dredging process, then the first step is, of course, if you have a trailing suction hopper dredger with a suction arm, tries to pick up sediment from the seabed, and it would take that material on board and raise the suction arm and then sail towards a certain location near shore, where at some point it cannot approach any further because of restricted water depth, and then it needs to pick a few options available for releasing the material. So one option would be to look at what we call in the Netherlands foreshore nourishment. So then we would basically place the material by bottom door placement on the shore face. But there is of course also an alternative. So you could go for beach nourishment, where you really want to have the material on the beach. Well, then typically you would need a floating pipeline to actually get that material to the beach, and actually where you can then reprofile it with land-based equipment. But typically, let's say this pushing through a pipeline requires much more energy than, of course, just opening the bottom doors. So what ways are there to calculate the energy consumption? Well, basically, almost any marine energy estimate calculation follows quite a similar route. So step one is that you want to understand how much power is required for different phases of this particular process, and also how long this power is applied. So if you know this for each phase, you can estimate the energy use of an individual discrete event, if you will. Well, if you understand the energy use, you can then translate it to the required fuel that you need to actually deliver this energy. And if you know how much fuel is needed, then you can use emission factors to estimate the amount of CO2 that is present in this fuel that is being consumed. So this is actually quite a common way to estimate emission footprints of all sorts of nautical traffic. And after the coffee break, I will go into a little bit more detail for inland shipping on how we have a PhD who's looking at this. But what is peculiar of dredging projects is that actually a lot of power goes into the dredging and placement phases. So that's why I've decided to highlight it for now. So if you want to estimate these different energy consumptions, then it helps to look at different phases, or first at the different power sources that are on board. So if you look at a hopper dredger, you can identify dredge pumps that are needed to actually create vacuums and suck the material from the seabed to actually get it into the hopper on board. You probably will need propellers to actually navigate the vessel, so either sailing full or sailing empty, but also during trailing, you probably want to have certain speed forward. You need jet pumps to actually jet water into the soil to release the material so that it can more easily be picked up. And you need bow thrusters to actually do more detailed positioning. So if you have a vessel that needs to connect to a floating pipeline, you need to make sure that it stays in position. And you have, let's say, the more regular board net or hotel power. Basically, that's the power that is almost always on for the lights and navigation and so on, things like that. So these components form the energy consumption of a trailing suction hopper dredger. So it will be interesting to look at these different phases or discrete events, which of these sources are actually used. So if you look at the dredging phase, then you see that all these sources of energy consumption are basically being used, except for maybe the bow thrusters. But if you go to the sailing phase, and then you typically will only have, let's say, the propellers operating to create sufficient forward speed, and of course the board net, because that's always on. And then if you look at placement, and then you might need your dredging pumps again, and your jet pumps to actually get the material off board, and maybe also in this case, the bow thrusters to stay well positioned at the floating pipeline. And if you sail back again empty, it's mainly propellers. So if you know these sources, then there are ways to actually estimate the amount of energy that this requires. So for now, for this presentation, it takes a little bit too much to actually go into those algorithms in detail, but I'm hoping that you trust me that these algorithms can be developed. And then you can go and look at different strategies for emission reduction. So which elements are in play? So it's interesting to distinguish a number of aspects. So first of all, there's things that relate to the project at hand. So there might be things that are peculiar for a certain project that trigger a certain energy consumption. There might be policy measures, so things that are more like in the context of the project, which are established by a local government or so to restrict what you're allowed to do. And then there are operational aspects, and those are more like the things that a vessel operator can actually control, or a project manager can control to change the way his project is executed. So typically those first two elements, you could view them as restrictions. So basically they box off the playing field. So what is given, and then that's defined by these aspects. And the operational aspects, that is, let's say, the freedom that you still have to, within this playing field, play around a little bit and try to optimize. So for this last few minutes to the coffee break, we'll first focus on things that you can do in the operational aspects. So that's typically a selection of work method and maybe the way you operate the equipment. And then after that, we'll briefly discuss these project aspects. And then hopefully I can show you that these different perspectives should always be viewed together to come up with the most ideal solution. But let's start with operational aspects. So if you look at this dredging project again, where a vessel comes, well, then you can imagine that, let's say, a big part of the energy consumption will be the pushing the material through the pipeline. That's quite energy inefficient, and it requires a lot of fuel. So one strategy that a vessel could take is to maybe take less cargo on board by which it will be less deep and by which it might be able to sail a little bit closer to shore and thus have a shorter pumping distance. And so you can imagine that that would save some energy, but at the same time, if you have less cargo on board, then you need to have more trips to actually still remove the same amount of material. So that might actually work against this energy saving a little bit. And an alternative to different uses of the same equipment would be to actually mobilize a different piece of equipment, let's say a smaller vessel altogether, which can already sail easily closer to shore. But then, of course, you will know that, that this will require many more trips. But which of these options is better than the other? Yeah, that's something you want to actually calculate. So for that, we did a case study, or I must say the student did a case study to look at a project for beach nourishment by a single hopper, dredging a little over 1 million cubic meters of sediment. And it had, let's say, a site on shore, on the beach, and it had a dredging site about 15 kilometers away and more offshore, and a connection point about 2 kilometers offshore of this beach nourishment position. And then if you calculate using all these algorithms that I'm not going into the greatest detail about, but hopefully you can take my word for it that you can calculate this, then you can basically for each individual discrete event, like loading, unloading, sailing full, sailing empty, you can calculate the energy that is required. And if you aggregate those, then you see that a project like this, so a little over 1 million cubic meters of sand, it will take about 31 days to complete and will have about 5 kilotons of CO2 produced. And of this, let's say a big part is in loading, a very big part is in unloading due to this long pipeline, and how do you call it, summed, let's say the sailing full and empty is also a significant part. But this is the way we can now sort of quantify a base case. Well, then you might want to play with different types of vessels, so a small, a large, a medium, or a jumbo type hopper. So larger the hopper, it might require less trips, but it will be able to approach the shore only from a greater distance. So how will this trade off? Well, then you get pictures like this. So you see that the larger the hopper is, the shorter the project will take, because of course it can take much more cargo on board per trip. So it will require less trips, so the project will be finished quicker. But if you look at the CO2 that is associated with it, then you see actually that it might have a larger footprint. And this is mainly due to the fact that it requires a lot of pumping through pipeline. So depending on what you want to achieve with your project, whether you want to focus on the cheapest project or the smallest CO2 footprint or anything in between, then you come in a trade-off situation really. And this is the way you can quantify this. Interesting here to see is that actually the medium hopper was our base case, but in this case, a larger hopper was performing actually better. And this was because of its hull characteristics, so that even with a larger amount of cargo on board, it still had a smaller draft in this particular case. So also in that way, selection of equipment can be really important. Well, then other things that you can do on the project is changing the vessel speed, for example. So in this case, we are changing only the speed, sailing filled or sailing empty. Well, then you see that, and probably you will know, is that if you look at the resistance a vessel is experiencing, that the larger the speed is, the larger the resistance is going to be. So this larger resistance requires more fuel and thus a greater CO2 footprint. So you see in the CO2 footprint, you see speed causes an increase in the footprint. But then if you look at the vessel speed and how it affects project duration, then obviously you will see that the faster a ship goes, the shorter the project will be. And this is again a trade-off. So are you looking for a fast project that maybe also be a little bit cheaper, or are you going to optimize on the CO2 footprint? And then somewhere in between, there's an optimum for every situation. So if we then take the reference case again as a start, then you can look at a smaller vessel that already can reduce the footprint quite significantly. And then mainly if you look at these bar graphs, because it can approach the shore closer, it will have a smaller distance to pump. So that affects, let's say, the totals of this particular example significantly. But then if you play with the speed, then you see, okay, the speed reduction, so from the base case is not extreme. So you see it mainly in the sailing full and sailing empty. Well, these were already not the largest contributors to the overall footprint, but so a reduction in those has only a limited effect. But if you then combine both, and then you can compare to the original reference case, you can achieve a reduction of, let's say, about 50% or so. 50% in CO2 emissions, but that you will probably pay for that into a much longer and more expensive project, right? But this is what you want to be able to trade off. Well, then we go to the other section of this problem, and that is if you look at what can, let's say, the project proponent or the government maybe do. So can they change some of the restrictions perhaps? Well, if we look into that, then this particular case, it's interesting to note that, let's say, the location of this offshore sand mining location, it is by law required to be outside of the -20-meter depth contour. And this is because the Dutch government is trying to keep the Netherlands strong against sea level rise. So it would be quite counterproductive if people would be mining sediment basically in the foundation of our country. So that's why they said, okay, the edge of our foundation is located at this -20 place. So this is a very sensible thing to do, but you could maybe also wonder, is -20 the holy number, or could -15 also be an alternative? So I'm not saying that one or the other is true. I'm just saying that if you want to investigate, and then you could do that by modifying this dredging location. So let's assume you could take actually a location around -15 rather than the -20. Well, then the mining location would become much nearer by. So your sailing distance would be reduced. Another thing that you might do is that maybe for this particular project, it was desired to, or required to actually do a beach nourishment, so that you actually had to implement this floating pipeline. But what if you could allow, let's say, maybe for application of sediment just near the beach, so in the coastal profile rather than actually on the beach? Well, in that case, you would eliminate this energy consuming transport to the pipeline, and you could place the material in the front of the outer bar, for example. Well, if you look at this picture again, you would see that the offshore mining location might come closer by, and actually maybe you could eliminate the pumping towards the beach. And then how would that translate to results? Interesting to see. So if on the one hand, we had, let's say, the operational elements that we could do, so it could save about 50%, but actually would be paid by a very much an extension in project duration. Well, the other part of the equation is to maybe be flexible on some of these items in the project, and that can also have a significant reduce in emission footprint. And in this case, not at a too large extension of the project. So what is the point I'm trying to make here is that, let's say, to actually fully understand this particular problem and to understand, let's say, where there's room for improvement, you need to basically take an integral view of this problem and try to quantify how different alternatives work, let's say, individually, but also later on maybe together. So how you can make a combination of things that in the end will be the most optimal solution. So yeah, this sort of summarizes that once more. So you can see, of course, that contractors, they might modify their work methods in the short term, or they might invest in new vessels with different types of fuel, for example. They could do that. But also clients, they should be aware of what they can do with their regulations and restrictions. So every restriction you impose that might trigger or might limit certain solutions that could be beneficial. So it would help to discuss this together to figure out what is the best way to address, let's say, emission reduction. And that can then be, of course, achieved on board, as I said already, with different fuels, different engine scrubbers, but also on the projects and maybe also even in the policies. And the whole point is, I think, from our ports and waterways perspective, is that what we try to do as a university is enable people to calculate all these different components and really study how those trade-offs actually operate in practice. So with that, I am exactly 1 hour underway. So this is a perfect moment for a break, but I will just briefly sum it up with this overview picture once more. So I was hoping that maybe you saw that topics like this hydrogen supply chain, or let's say the shallow water effects, or the emission footprints on the network, or the trade-off in dredging strategies, that they might seem like different elements altogether, but it's clear that they are all somehow related to supply chains that operate on water. And we see, let's say, a very common approach in all these problems. And that's why we have developed tools like we did to analyze those. With this, I'm concluding my first hour, where I hope to introduce you into ports and waterways the way we view it at TU Delft, and how that actually materializes in some of these research topics. And then after the coffee break, which we'll have to negotiate in a bit how long we take for that. But then I would like to introduce you into 3 PhD topics that we are currently working on, and that dive into some of the topics I addressed already, maybe with a little bit more detail. And then you will know what kind of research we are doing, and hopefully maybe you'll learn a little bit about those topics along the way. So with that, Pablo, I'd like to basically finalize this first hour.
Perfect.
And what is, let's say, a good moment to reconvene? How long will we take?
What do you prefer, Mark? 5 minutes, 10 minutes?
Yeah, maybe we can do 10 minutes, and people can just refresh, maybe have grab a cup of coffee. So let me see, then we would reconvene at, and in 10 minutes, right? So 10 to the half hour.
Exactly. Well, thank you, Mark, for this very interesting first lecture, and see you in 10 minutes, all of you. Please stay in the meeting hall or on YouTube, just to keep following us.
Yes.
Thanks.
Okay. See you in 10 minutes.
Yeah.
Okay. Let me minimize this one first.
Okay. So welcome back, everybody, and let's continue with the second hour. Mark, all yours.
Thank you, Pablo. Yeah. So so in front of the coffee break, I introduced the way at port we view ports and waterways issues at TU Delft, and I try to illustrate how we look at it is integrated systems, and that we think quantification is quite important, and we highlighted some master theses that could illustrate that. And in this second hour, I'm going to address a number of our ongoing PhD studies to bring a little bit of additional color to the type of research that we are doing. I could have probably included maybe even more PhD topics, but I thought, okay, better to treat 3 topics with a little bit more length than to treat lots of topics very briefly. So this is why I picked 3 topics the way I did. And then at the end, I'm going to try and give a little pointer forward to tomorrow an equally interesting presentation by Alex, and the day after tomorrow by Fedor. Let's go into the first, the first PhD topic that we are working on. So together with my predecessor still, Tito Vellinga, I don't know, maybe some of you have met him and know him. We together guide a PhD student, Frederik Vink, who is looking into the effects of high and low discharge extremes, and then typically we associate those with climate change, and we want to understand what the effects of those discharges are and how, let's say, possible mitigating measures could be designed and assessed. And Frederik is part of our team, but he is also working as an advisor at our Dutch Ministry of Public Works for Rijkswaterstaat. So he's basically sort of doing a PhD study that is quite relevant to his actual day-to-day job. The intros basically into this particular work were a few noteworthy events. So, for example, in 2018, we suffered a very, very, very dry summer, actually in all northwestern Europe, and what that caused. And then here you see it's unfortunately in Dutch, but it's like the average over 13 stations that records the precipitation in the Netherlands. And then you saw that, let's say, there's a big shortage of precipitation developing in 2018, and in particular from, let's say, August onwards. And this lack of precipitation that translates to lack of runoff basically into the rivers, and then that in the end translates to a lack of discharge, and that looks a bit like this. So here you see the Lobit entry point where the River Rhine is entering the Netherlands, and well, there's just stations available that record in cubic meters per second the daily average discharge at this point. And then you see that typically over our winter time, you have high discharges, and then it sort of drops off a little bit into the summertime, and then normally it would go up again in the winter. But due to this prolonged drought, you see that actually the discharge is reducing and reducing and reducing even further. And this horizontal line at 1,020 cubic meters per second, that is, let's say, our threshold where we say, okay, below that particular discharge, it's likely that problems will occur. And you can see that actually there's I think it's like 124 days or so that the discharge was below this level. And so for several months, the discharge was really, really low. And at the same time, this was a thing that happened only a few weeks ago, actually, just before the summer holiday, so in July here in the Netherlands, where there was all of a sudden in the normal summer period, so which is normally a bit more dry, you saw all of a sudden a massive rainstorm develop, which covered not only the Netherlands, but also large parts of Germany and of France and of Switzerland. And actually so much rain fell in such a short period of time that it caused a massive increase in discharge for a period of time. And that looks like this if you look at the discharge graph. And then you saw that after this rain event, and then for a few days, the discharges on rivers in the south of the Netherlands, they increased to levels that we would normally only see in winter times maybe, and only very rarely, and then it would take a few days to die off. So compared to the drought, a much shorter period of time, but still quite an extreme increase and decrease of discharges due to a massive rain event, and which we probably also associate with changing climate. And so we expect actually this kind of events maybe to occur more frequent. So if you look at newspaper articles, so they are in Dutch, but I will translate. And then if you look at the drought, and then you saw pictures like this, where basically the water had receded quite drastically, and there was very limited underkill clearance. And here we see that construction raw materials became much more expensive. due to the fact that they could be less efficiently be transported over with inland shipping. And actually there were also quite some concerns for industries in Germany who relied on the supply of their goods from imports from overseas that come via Rotterdam and then over the River Rhine. And yeah, their supply of fuels and raw materials was actually impacted for this period of several months. And if you look at the flooding, and then you see different type of messages. So this was one that caught quite some attention, where you see, let's say, an inland water transport vessels with a few layers of containers on top of it. And there was quite some excitement where people were thinking that it was going to hit this bridge. And then in the end, the captain said that he still had like 30 centimeters to spare, so I was really confident that he would make it. But for high water, yeah, then typically you see that the air draft, so the distance between, let's say, a fixed bridge and the water level, that becomes a problem. But in both cases, either too little water, so the draft is an issue, or too much water, that the air draft becomes an issue. It's still interesting to figure out how those occurrences will affect the transport supply chain. So for that, this PhD student is looking at how he can relate the status of rivers under the influence of changes in discharge scenarios, and how he can translate that to changes in depth, width, and height, and how that will then affect performance indicators of the supply chains. And then a number of performance indicators are the number of trips, the total transported volume, and something related to cost. So if you look at the effects of discharges on depth and air draft, and then here you see a schematization. So if you would normally have a river cross section, then it would have a certain profile. And probably you want to understand how, let's say, at a certain water depth, which can still be navigated, what the width of the channel is, to know, for example, if, let's say, still two vessels can pass each other, and if there's not enough space, maybe cargo needs to be offloaded to actually become shallower, right? So that's one of the things that we want to understand. And in Delft, we do a lot with hydrodynamic modeling. And one of the models that we use a lot is, for example, SOBEC, which is a 1D water transport model. And it typically solves this, the 1D shallow water equations integrated in width and depth. But then it also has information about the river cross-section all along the river schematization. So if you have a SOBEC schematization of a river, you can know the changes in the water levels, and then with these profiles, you can translate it to available water depth and channel width. But at the same time, you can imagine that if the water levels increases and you have fixed bridges, then yeah, you're interested in the distance between, let's say, the under part of the bridge and what will be the effect on the maximum loading capacity. So what could be is that actually a vessel needs to load less containers, maybe remove one layer to be able to fit under the bridge. And so those are things, and those are aspects how changes in the water system will affect the performance of the supply chain. And then we have, let's say, a number of observations from which we can learn. And then one thing that is logged is, let's say, all vessels are counted at certain positions along the waterway. And here you see, again, the time horizon, where in this period you had this increasing drought occurring. And then you saw that the number of trips of all vessels together, it would increase. But what is also interesting to see is that some vessels, they increase during the drought, but some vessels actually stop operating during the drought. So how the fleet composition changes during the upcoming and falling water levels is quite essential to really be able to model how your system behaves. Well, the other part that you can get from these counting points is, let's say, the total amount of transported cargo. And then for dry bulk, we could see that even though over this period the number of trips would increase, and that then still, let's say there are more trips with less cargo, and then all summed together, the maximum transport capacity still reduced of this particular, for this particular type of cargo. And then if we translate it to cost, so in this case, I will go a little bit quick over it, but we can see, we can know that there are massive impacts on transported costs from also all sorts of news messages where, for example, in the German hinterland, steel manufacturers, they were really complaining about losing fuels for their factories, but also raw materials. Also, industry suffered an estimated 4.7 billion euros of production losses. So that's also serious impact. Well, it was, so there are different estimates of what kind of cost should be associated with a draft in the Netherlands in this case. And so you can imagine that there's these droughts, they can have quite a big economic impact, and then that could warrant actually for the government to look at different ways to intervene. So how can they make the system more robust to climate change? Well, for this we used, among others, our open CLSIM model to try and reproduce these observations. And one of the things that we try to do is estimate the transported volume per week and estimate the total number of trips over time. And then there, you see a few discrepancies between what the model says and what was observed. So for example, here you see that we anticipate in our model that less cargo is being transported during the very low water levels. And this can be explained by the fact that we have implemented triggers for reduced loading in our model, which are basically fixed underkill clearances, like 30 centimeters for sandy bottoms and 20 centimeters for sandy bottoms and 30 for more hard bottoms. But then we see in practice that, let's say, captains, they try to maybe load a little bit more than this kind of level, because they believe that by knowing more details about the river, they can find a path that is still navigable. So even though the model at some point says that no more cargo can be transported or less, then typically in practice you see that people become inventive and they will find ways, or either take more risk or find ways to still navigate this system. And another thing that is striking is that our model basically very quickly responds in the number of additional trips when the water level drops. And why this is not happening in practice is probably because in our model, once the triggers are exceeded, we can immediately get additional barges and vessels because it's a model. But in practice, typically it will take some time for people to maybe get those barges at the proper location and actually integrate them into the supply chain. So these are differences, but we think that they are explainable differences. So we're quite content about the way we are able to reproduce what is happening on our waterways. And actually we can also do that for different parts of the fleet. For different vessel types, we can have quite a reasonable reproduction with some anomalies, but that's stuff that we are working on. So we have quite a good idea that if we can simulate, let's say, discharges, different discharge scenarios on our river system, that we can translate that to how the fleet will change and adapt itself, and how that will translate to more trips or cargo transport. So with that, we will have a tool in hand, we believe, that will allow us to compare, let's say, different measures, different interventions that the government could take to actually improve the situation. And what kind of things are people thinking of? Well, there's a range of things. So you can imagine that maybe parts of the river, if the number of droughts becomes too big, and that maybe we need to look for ways to regulate the river by creating maybe weirs in the system to have more water depth available, or maybe create let's say side channels that allow for, you will have, let's say, the passing of the lock to take into account, but there will be more water available, hopefully, so it might be good for the supply chain, or these, how do you call it, shore parallel dams, that hopefully can keep a greater water depth in the river, even with lower discharges. And another option is, of course, to do some dredging to remove possibly a number of bottlenecks in the system. But all these interventions, they of course require quite substantial investments. So you need to figure out if it's going to be worth it. But there are also measures that you can think of in the logistics chain. So maybe you can change the sailing regime. So maybe there's still more moments in the day where you can even fit more trips, if that is, let's say, a thing that could still be in play. But you could also maybe think of possibilities to perhaps increase stockpiling. So if you can anticipate that a certain period of drought might come into play, and then maybe you can transport already a little bit more so that you will have a stockpile as a buffer basically for the drier periods. But we found out that typically, if you have a really long drought period, then it's not practical to store so much material in an increased stockpile. But maybe you also can think of, let's say, transfer hubs, where maybe you can have a larger vessel move goods up to a certain point, and then maybe other smaller vessels or so, or different modalities might be able to take over. Those are all things you can think of. Yet another measure you can think of is modifications to the vessels. So you can perhaps apply buoyancy devices next to the vessel so that it actually becomes higher in the water column. Or also people have been looking at ways to reduce the lowest point of a vessel. So typically the propeller and maybe the tube around the propeller, that can be limiting factors for the maximum depth that the vessel has. And there are some people looking into different vessel shapes that might perform better at these low discharge situations. But it's always good to remember that even though a vessel might perform better in the extreme situation, then it's really a question mark still how it will perform in all the rest of the situation. So during normal situations. So that's again a trade-off that you want to be able to investigate. And then of course, a final measure that you can take is to invest in information services. So maybe better riverbed predictions or riverbed data sets that allow captains to maybe have a better idea of how much cargo they can put on board, predict water levels maybe further in time than we do at the moment, etc. So there's a whole bunch of measures that you could take to robustify, if you will, your network against climate extremes. But one of the things that we want to do is to be able to calculate how, let's say, one intervention, maybe it will have some positive aspects, but what are the negative aspects? Well, much like this dredging example from before the coffee, we want to understand, let's say, the solution space and understand which measure or which combination of measures is going to perform best. So this is one piece of work that we are doing, and I can imagine, so I did not link it now to, let's say, local issues that you might experience in your setting, but I understood you also have, let's say, a very large river that plays an important part of the inland transport system, which also has varying discharges. So I can imagine that quite a similar concern might occur here. Right, so I list here these mitigation measures still in one slide, and you probably want to understand how, let's say, sets of measures together may be the best way forward. Well, a second PhD that I'd like to introduce some work about is Man Zhang. So she's doing her work on basically that the energy consumption and emissions that follow from waterborne supply chains, but with a special interest into also the energy transition. So one thing is to already know what is happening with the current types of fuels and engines, but we also want to be able to understand if you use alternative fuel sources, so maybe battery electric containers or hydrogen as an alternative, or other types of fuels, that those different settings, they might affect the sailing range, because maybe they have less energy content in their per cubic meter or per ton, but they might not just affect, let's say, the sailing range, but maybe also the amount of payload that you can take on board. If, let's say, maybe an electromotor takes up a large amount of space, and then maybe you can take less cargo on board, and maybe you can have a smaller sailing range. So how do such effects then translate to the performance of the supply chain? And also, how could you actually set up a bunkering structure for different types of energy carriers, so to say? And that's the topic of her research. And basically, the way she is approaching this is by basically, again, looking at these resistance calculations, so trying on based on vessel properties and fairway properties to estimate the resistance and the required power, and then the fuel consumption. But then also she focuses a lot on how this interaction between the water system and the vessel actually takes place. So we'll give some examples of that, and then reiterate how you could project things that you can calculate for one vessel, how you can project that to an entire corridor with a whole bunch of vessels, right? So it's just calculating it for each vessel and aggregating the results, but I will come back to that in a second. So if you look at the estimation of energy consumption and the related fuel consumption, then basically we have in our OpenTISIM package, so our network simulation package, we've integrated a bunch of algorithms that stem from partly from Holtrop and Mennen, who defined a method to relate ship resistance to speed to ship resistance and energy requirements, but also some updated research that's been done here at TU Delft to better estimate the effects of really, really shallow water beneath a vessel, the method by Zeng. Basically what it does is that if you have as input information about the ship's dimensions, so the length and the width and the draft, and you know something about the vessel's speed, and you know something about a fairway's characteristics, so typically you want to know the water depth, and if there's a current there, then you can use these Holtrop and Mennen and Zeng and Karpov methods to calculate the resistance that a vessel experiences, and how much power it needs to overcome this resistance. And then if you need to do that for a certain stretch of waterway, how much energy in total that requires. And if you know that, then through specific fuel consumption and emission factors and properties on engine age and engine performance, you can translate the energy requirements to either fuel consumption or to emissions. That's basically how this method works. So I'll get into it in a little bit more detail. So if you look at the resistance calculations, here we used, as I already mentioned, we used a very old method by Holtrop and Mennen that many people probably are aware of and use. And we've added some more recent algorithms that have been published. Well, typically Zeng is more recent. Karpov is actually even much older than Holtrop and Mennen. And basically the way it works is they try to estimate the total resistance from a number of components. So the friction resistance, the wave resistance, the resistance related to appendages, and things like the residual resistance. So if you calculate that, then you will know basically the amount of power that is needed to move a vessel at a certain speed. But then it's still a puzzle to know how much power you then need from an engine to actually have that much power in the propeller. So for that, there are also a number of rules of thumb available where you can go from the effective horsepower that is needed to go a certain speed. Then you can, with loss factors, calculate back how that would translate to the delivered horsepower that is delivered to the end of the shaft. And then you can calculate with yet another few loss factors, how you can translate that to the power that's delivered just behind the engine, the power at the brake, as it's called. And by translating with these loss factors, you can figure out, let's say, the power required to overcome the resistance to the power that the engine needs to deliver. And that's typically higher than the power that you find at the propeller because of these losses. And then if you know the power that is needed at the brake, you can figure out, let's say, what kind of fuel you need to actually deliver that power. But next to, let's say, the power related to propulsion, there's also a component, what we call hoteling or a board net, as just before the coffee break. So that's like the lights and for navigation and the refrigerator and the coffee machine. So those kind of ongoing powers, and those are for inland shipping in this case estimated to be 5% of the installed power. And then by taking these assumptions, you can estimate the power that's required by a vessel to sail a certain stretch at a certain speed. And then if you know that, you can figure out how long does this vessel take to sail a certain stretch at that speed. And then if you multiply the power that is needed by the time it needs to be applied, you can get the energy that is consumed on that particular stretch. And once you know the energy that is being consumed, you can use other literature to translate the energy that is consumed to the fuel that is being consumed by applying so-called specific fuel consumption factors. And then next to the total emissions that you can or the total fuel consumption that you can then expect, you can also calculate what kind of emission are associated with that. And there are a number of factors that we've included in that. And that is, let's say, depending on the engine age, let's say there are different relations between, let's say, the required power and the fuel that is being consumed. So you see that newer engines, they require less fuel consumption to deliver a certain amount of power. And also, if you look at emissions, and then typically the CO2 has a quite strong relation with the fuel consumed, but especially for newer engines, they are much more efficient when it comes to particular matter emissions and nitrogen emissions. So the engine age is an important factor, but also how this engine is used. So if you are typically in the 80% or so engine capacity used, and the engine is most efficient. But for example, if you're waiting in front of a lock, then you probably have a much less effective engine load, and that typically translates to significantly higher emissions. So the engine load and the engine age are important to make good assessments. Well, then to apply this, so this Monjang, she applied this in a paper. She's almost ready to submit to, let's say, a number of prototype cases. So here we have, let's say, a river with a certain bed or a certain depth and a certain current. And then we have, let's say, a river section of 300 kilometers long, where at first it's equally deep everywhere. Then the second case is there's a limited water depth in the middle. And the third case is even a more limited water depth in the middle, and where the first water depth limitation basically only limits the draft, but still can take the fuel load. And the third case example is so shallow that actually some of the load needs to be removed. So that's interesting as another case. And then basically by applying these calculations or these algorithms, you can estimate, let's say, the amount of fuel that's being consumed or the amount of power that is needed for certain vessel speeds. So you see that the faster the vessel goes, the more fuel it consumes, as you might expect, and comparably that links to the emissions, which you see here below. So far, no real difficulties yet, but what if we go to the next case where you have, let's say, a shallower area in the middle part, and then you can you see the dotted lines, they are assuming, let's say, a fixed velocity, and the continued lines, they are assuming a fixed engine power. So you can imagine that if a vessel sails through shallower water and it experiences a shallower water, then the resistance will increase. So actually you will need more engine power to maintain the same speed. And that is what this dotted line shows. So if you try to maintain the same speed, but the underkeel clearance has been reduced, well, you require a lot more fuel. The other way around, you could actually also say, okay, I'm going to keep the same engine setting, so the same power, and then I will just sail over this shallow water area. And then basically what happens almost automatically is that as soon as you experience more resistance, then this will cause the vessel to slow down. So the vessel will, with the same engine power, the vessel will move slower over the shallower area. And because it takes longer over this area to complete, you still see this little rise in emissions compared to the natural situation or the undisturbed situation. Well, just to show how these routines work. And then let's say maybe the third example where it is so shallow that people even need to offload certain amount of cargo. Well, then you see basically that compared to the previous one, I'll flick back and forth just quickly. You see that the increased fuel consumption, it only increases further, right? So this is you can now see that with these algorithms, you can actually quantify the effect of low water depth on the fuel consumption of a vessel. And then also this shows that if you move over a certain river stretch, then you can account for changes in water depth from stretch to stretch. So that this is quite important because we really would like to be able to estimate energy use and fuel consumption as a function of space and time. So that's why we want to have this type of capability. Well, here's another similar picture where we look at, let's say, here we accumulated, let's say, the fuel consumption, for example, for 3 different sections. So let's say these colors, they are, let's say, well, maybe if I move here, so they relate to the first section, the second section, and the third section. And in any case, this middle block is always related to the shallowing part. And then here it says, okay, what do we calculate if we do one trip with no current, or one trip upstream and one trip downstream, and then the round trip. And then here you can, this way you can compare, let's say, what the effects are of sailing with the current or against the current. And here you can see that if you have a shallowing, then in any case, these middle parts, so the fuel consumption over this shallower part, that will completely dominate this energy consumption and also the emissions. So that, well, that goes to show what you can do in terms of capability. And here you can also see what the effects are of engine age influence. And so we see that as the engine age becomes newer and newer, you see a little bit of a gain in terms of efficiency. So the engines have become a bit more efficient to generate power with the same amount of fuel. And since CO2 emissions is almost directly related to fuel consumption, you see that also the newer an engine gets, you see the same trend in CO2 emission reduction. But what is quite striking is that, let's say, especially newer engines, they perform much better when it comes to other environmental pollutions like fine particle emissions. So like PM10, for example, the more recent engines perform drastically better than the older engines. And something similar is upcoming also with the nitrogen oxide emissions. So it's less steep than the fine particles, but still you see this trend, a stronger trend than CO2. So now if we can use this to analyze how corridors work, then basically what we do is we just take all the vessels that operate on a corridor, and then for every vessel, we will get these kind of logs, basically which log, let's say, a starting time and a stop time when a vessel is sailing on a certain section of the waterway. You will know also the start and stop location of that particular section. And then with that, you can calculate the difference in time and the difference in space. So you will know, let's say, basically the speed that a vessel takes, and then you can translate it to the power that is used and to the emissions. And by knowing this on the different sections, you can aggregate the contributions of different vessels to the relevant sections and then get heat maps more or less like this, where you see, okay, for the current traffic, you will see the most emissions in terms of CO2 at these locations, for example. And what is striking here, you see these little dots, and these little dots, they are actually locks. And what you see that around the locks, vessels dwell for a longer period of time. They use their engine to a lesser efficiency because they are not sailing at 80% of their capacity. And then you see that, that you will get hotspots of emissions on those locations. So that's something you might want to avoid. So if you can reproduce, let's say, the T0 scenario from, let's say, AIS data that you have on the network, well, then you can also play around with the model to test different policies. So you could play around with policies to see if around the locks, and then particularly the waiting area, so not really in the locks, but in the waiting areas where vessels are dwelling for a longer period of time, if you would supply shore power there so that people could turn off the engine, how much would you then save? Well, then here you can calculate the T0 situation and the situation with shore power. Well, then you see that the impact isn't super dramatic. But then another option that you could do is say, okay, what if we would replace all the vessel engines on this particular network that are older than 2007 and replace them with the newest stage 5 engines? Well, then you get already a much bigger impact. So here you see that, let's say, the impact on CO2 is not very large. And that's quite explainable due to that picture that I just showed, but especially for fine particles and NOxs, you see that actually has a big impact. So it looks like investing in engine upgrades, let's say, that could be a method that could have a lot of impact. And another could be to have, let's say, local speed limits to see if maybe around particularly sensitive areas, if you would limit the speed, what would that do? Well, you see that that also has, let's say, some form of a reduction, but it's good to realize also that, let's say, if you reduce the speed limit, then it will also take longer for cargo to be transmitted from A to B. So it also has a lot of side effects, but this is just to show how you can test different policy measures in a quite quantitative way by applying this method. So this is definitely work that we are continuing, and it looks like a very interesting method to support policymakers. Well, then the final example that I want to discuss with you is work by Floor Bakker. So he is a PhD candidate in the framework of a large research program that was started here as the main applicant is TU Delft, but basically every university in the Netherlands is involved. And it is looking at the potential for salt intrusion occurring as a consequence of climate change. So we've seen that rising sea levels and changing discharges that might actually cause salt from the sea to intrude further inland. And that might actually impact our potential for agriculture, but also our freshwater uptake and so on. So to investigate that issue, which will occur not just in the Netherlands, but probably in more places in the world, we started this salty solution project. And in this salty solution project, people are looking at different ways to mitigate this salt intrusion. And Floor is actually focusing on how can you translate the effects of these different measures to port logistics. So what kind of effects could you actually foresee, and how can you show how, let's say, a certain measure that is positive to prevent salt intrusion, how can you quantify what the effects are on logistics, for example? Well, to do that, he basically looked at two situations. So you can hopefully see some reflection of our previous picture of the ports and waterways overview. And Floor is looking at two cases, an open system. So that's a system where, let's say, the river is in direct connection to the sea, and let's say a port is indeed exposed to maybe salt wedges entering and leaving and so on. So the open system, and you can have a closed system where actually there's a lock in front of a port complex. So there's a control about how much salt is actually entering the system. But both these cases are of interest. And so for that we look at, so for example, looking at port accessibility for these salty type solutions. I want to show an example, and this is an example that actually Sebastian Iglesias is doing his master thesis on also. And here's where we have, let's say, a port. So in this case, it looks remarkably like the port of Rotterdam. And that's not really a coincidence, as this is one of our main case examples, but it should be applicable to other ports as well. And actually in this particular case, you see that if you have a port complex with all sorts of terminals with berths and so on inside the port facility, then you see that vessels that try to enter towards a certain terminal, and they might face, let's say, periods where, let's say, the water level is so low that they cannot actually access. So this is when what we call a tidal window. And so you can have tidal windows related to depth, but you can also have tidal windows related to currents, when the currents are so large that, for example, a vessel cannot make this turn safely because it would experience too much side effects. Well, then one of the options you could do to mitigate salt intrusion would be to reduce actually the water depth in this access channel. So maybe if I flick to and fro, and you can see here before it was quite deep. And what if you would have a scenario where for the purpose of reducing salt intrusion, here it would be shallower. Well, then if you have, let's say, if you have a terminal here that experienced the tidal window, and then you will see that if you had a larger tidal window when it was all open, and now it's shallowing, then let's say this tidal window is narrowing, right? The period where there's sufficient water depth becomes shorter. And that will have effects on traffic intensity, sailing times, but also maybe the number of encounters. So if the tidal window is shortened, then maybe more vessels want to make use of it at the same time. So that could affect the safety and so on. So these are the things that we try to investigate. And when it comes to, let's say, terminal performance, you can imagine that maybe smaller tidal windows, they will affect maybe the terminal occupancy. So maybe the terminal cannot operate because a vessel cannot actually access in time. But at the same time, it could also be that a vessel that is actually ready to sail out cannot actually leave because its tidal window isn't available yet. And so these things we try to quantify. And another thing that might be affected is, of course, the occupancy of anchorages. So that if you have smaller tidal windows, and then maybe your queuing will increase and your anchorage areas will be full. That could be the case. So we want to investigate how that works. And then the second case is related to closed systems. And there we basically have a lock in the entrance of a port, and that will affect, let's say, the salt intrusion, but it also causes delays, of course, for a vessel that wants to pass it. So if we look at how Floor is going to analyze this, he's using, again, our transport network simulator, and then he's sort of schematizing these networks throughout the port, where you have, let's say, different water depths and different vessels going from A to B to actually get their cargo unloaded. And things that you can then investigate. So if you look at this particular plot here on the left, you see, maybe, I don't know if this blocks view, but then you see here on the x-axis, you see at the distance it takes from, let's say, the entry of the system and then towards the berth and then back again. And here you see time. So each line is a vessel that's starting to sail into the port and then lying at the berth and sailing out of the port again. And then if you have numerous vessels following each other, then you can see that at the beginning, let's say all key lengths were free, but then as the vessels come in, key lengths are becoming occupied. And in this case, the setting was such that there is no real depth tidal window and also no real current tidal window. So basically all the time, the port is accessible. But now, of course, it's interesting to see what would happen if you would reduce the water level a little bit. So that can be, of course, man-made, but similar could be if you have, let's say, lower discharges by which the water levels drop, and then basically it's like the same effect that is happening. And then you could get a picture like this, where basically in the red, that's when, let's say, you have either a tidal port, so like a depth tidal port or a current tidal port. And then as soon as here there's inavailability of the access channel to be sailed through, then you see that the vessels, they cannot pass, right? So all the traffic is concentrating in the green part. So you see that these tidal windows, when they occur, they push vessels basically together to actually make it in time. And it could actually be that they cannot make it in time and then have to be in the queue to wait, right? So in this way, you can see that these tidal windows, they have a deteriorating effect on the performance of a port. And if you would even go further and make it even more squeezed, and then you can see that you get a really strange compressed traffic situation. And then in the end, it will most likely really affect the capacity of a terminal and of a port to actually get the cargo moved. So these are just, let's say, some examples to illustrate how these analyses work. But actually, of course, we want to try and apply this to more real-time situations and then investigate the trade-off between investing in maintaining, let's say, a lower bed level and thus a greater accessibility versus the cost and the salt intrusion. Well, by applying these kind of models, we can really quantify how this trade-off will work in practice. So for the closed system, let me see if I can somehow. For me, this is in the view, but I'm hoping it's not blocking your view. But let's say for the closed system, and then we're not so much looking at, let's say, this tidal ports, so the depth or the current tidal ports, but we're literally looking at lock complexes, and they typically have a waiting area where vessels that are approaching the lock and need to wait until they can actually start entering. And if they enter, they go into the lineup area, then they move into a locking chamber, wait for the leveling to occur, and then sail out again. And then by simulating the time it takes each of these individual steps, you can quantify the delay, for example, that the lock is causing on a vessel that is passing. So one of the things that we can do with this open TISIM model is to, just like we had these time distance diagrams for the port, well, we could do a similar time distance diagram for vessels passing the lock. And then you can see that a vessel is approaching, and then it can sail into the lock chamber. It has to wait for it to level, then it can sail out. And then as soon as it is out and past a certain element, then let's say a vessel coming from the other direction can sail in, and so on. And by this way of quantifying, you can figure out how traffic is moving through a locking system and what kind of delays are associated with it. And why do we want to know this? Because if you calculate it in this way, you can calculate things like how long are the doors open between vessels going in and vessels going out. So you can imagine if one vessel comes out and one vessel goes in, then the time that doors are open is much shorter than if 3 vessels need to come out and 3 vessels need to come in. Well, the longer the doors need to be open, the longer there is time for the salt and fresh water in the lock area to exchange. and the larger the impact of a locking cycle on salt intrusion will be. And yeah, the reason why I included this is so-called a locking exchange formula that's been developed by Delft, by Otto Weiler et al. And there things like the door open time and other parameters that we can now quantify, they can be used to sort of estimate the salt exchange, and then they can implement that into 1D network models, for example. So then based on, let's say, the locking process, you can get a source of salt entering the model, but it could also work the other way around. So if you are only allowing a certain maximum amount of salt to exchange, then that could actually cause, let's say, traffic regulations that restrict the number of lockings that can take place. So well, investigating this interaction is exactly what we can do in this case in a quantified way. And this is work that Floor is working on. So we are nearing, let's say, the end of this second hour also, as far as I'm concerned. So before the coffee break, I introduced to you what we are doing in Delft when it comes to port and waterways. I shared you some of our foci on education, so looking at it as an integral system, but also focusing a lot on data and coding, and illustrated that with some MSc topics. Then after the coffee break, I showed 3 PhD topics that are currently ongoing. We have a few other PhDs working on similar topics, and they are also trying to really take a system approach and then try to quantify what is happening in the system and how you can, how you can analyze the trade-off of different measures when it comes to the costs that are associated and the likely impact that they might have. So that I hope that this clarified a little bit what we are doing at the Ports and Waterways section. And of course, I can always recommend that you read our open textbook if you want to learn some more about it. But that's basically what we are working on at the moment. And I promised also to have the briefest outlook on the next 2 port lectures. So tomorrow we will have our associate professor, Alex Kiricek, who is working in our group. And he will tell you something about sediment management and accessibility of ports. So it has some relation to the work of Floor Bakker that I just told you about these tidal windows. But Alex is approaching it also much more from the sediment perspective. And he's looking at the effects of sailing through fluid mud layers and much more looking at the geophysical properties of mud and how that affects waterborne transport. And the day after that, we'll have a presentation by Fedor Baart, who is, let's say, a senior specialist on data science at Delft, but he's also working in our group for 2 days a week, and he's helping us with simulating techniques and new approaches to data science and so on. And hopefully he can introduce you a little bit into our digital twin thinking, so that maybe you can see in a little bit more detail what is possible and how you can actually use that to analyze your own network situations. So with that, well, I am, I think, more or less exactly on time, if I'm not mistaken. And that's the end of my 2 hours talk.
Hey, Mark, thank you very much. It was an impressive outlook of all the work you are doing at TU Delft. I think really insightful of everything. So thank you for that. Well, we have, I think, some time for exchanging some questions, comments. So far, we have a comment now here on the chat from Carlos Gines. Carlos, would you like to share your comment directly with Mark, please? Carlos is one of the professors from one of the universities in the south of Argentina, and also our Marcom delegate into young Marcom delegate of Argentina.
Young colleague.
Yeah, thank you, Pablo, and thank you, Professor Koningsveld, for the lecturer, very interesting. And not only is just remarks and points. One is the philosophy of Professor told us about the book and in fact of the way they have to face with, in this case, port problem or port logistic problems. But I think that simulation is a tool that you can easily use, not easily, but easily use or extend to other fields of the real life. And mainly it's an interesting tool for the decision makers. That's interesting for us in our country, especially, I think. And well, congratulations, and that's all. So I was involved in simulations during my Master of Science in IHE, but in 90s with Professor Grunfeld. I don't know if you know him. And well, that's a very interesting tool, I think, just to apply in any place. Thank you very much, Professor, and thank you for all the assistance to this lecture.
Yes, thank you for your comments. And of course, yeah, I completely agree that that indeed it's a very powerful tool, but not only, let's say, for decision makers, but sometimes also, I think, for researchers to understand, let's say, how things that they know in great detail about a certain subject, how it might be of relevance, let's say, in a practical problem. So I think the way we always try to approach these simulation settings is to do it in such a way that it brings together, let's say, specialists that know something specific about a process or something that is happening in practice, and then show through simulation how that will affect, let's say, system performance under different measures. And then, when done right, it can be a really strong communication tool to facilitate the discussion between scientists and decision makers, I think.
Yeah, thank you. I agree. Yeah.
Well, thank you, Mark. Thank you, Carlos. I think, Sebastian, you have your hand raised. So,
thank you. First of all, thank you, Mark, for the presentation. Just wanted to do a small reflection also in line with the application of simulation models. First thing I thought is that there is a large difference between the application of these digital tools in Argentina compared to the Netherlands, for example. But then I also thought, despite the bridge, how easy we could apply those sort of tools. First of all, these are open source tools, as you explained, Mark. And secondly, the cases that you explained are also important for us in Argentina. So maybe, I don't know, maybe somewhere else here in this group could raise an issue in Argentina and say, hey, for example, I don't know, maybe Frederick's research on climate change could be applicable to our waterways. So
so you're of course let's say a first-hand experience guy, because you are basically working on it yourself. So you've seen for the cases that you are working on that as long as you have, let's say, AIS data or some information about the fleet operating and some information about the status of the network and how it changes under different conditions, then it's already quite easy to bring, let's say, the existing tools to application to a new setting, right? So as long as you have your network of the waterways and some idea about the type of vessels and the type of cargo they bring, then it's quite, I think, quite close to apply it in a new situation. We set it up in such a way that all the code it uses lot and long coordinates, so it should be applicable everywhere in the world. And also working with different, let's say, time zones and so on. That's all done as generic as possible. So it should be applicable, I think, to other situations, even though it may take some effort. But it would be quite interesting to see what is needed to do that. So I believe that it can be applied quite generically.
Well, thank you, Mark, and thank you, Sebastian, for raising the topic, because when you were presenting, Mark, many things came to my mind. Nowadays, we are facing a second year drought, extreme drought on the Paraná River, with consequences on seagoing vessels, but also on inland barges. 5 years ago, we had the second highest river discharge in the history, so extremes are getting closer. So perhaps it will be interesting and something to discuss later on how we can address these topics or replicate or adapt these topics to our situation here in Argentina, perhaps in a joint research program or with some colleagues.
Yeah, it would be really interesting, because I think indeed, let's say the climate change problems, they're probably quite similar, but I think the characteristics of the Dutch network versus the Argentina network are probably a little bit different. So of course, I don't know all the details, but I think in the Netherlands, there's quite a clear distinction between seagoing vessels going up to the port of Rotterdam and then inland shipping vessels taking care of the hinterland. And I think in the Argentina case, you see that seagoing vessels with adjusted loads, they travel much further inland. So it's a different situation, but the type of problems should be investigatable with this kind of tools, I think. So that we
yeah, really definitely. Yeah, we can discuss further on how to move ahead in this. Like seagoing vessels, as you may know, go inland country 800 kilometers here. Yeah, so well, that's interesting. Following up, there's a question coming from our audience on YouTube. So I will share it with you so we can answer Victoria Souverain. She first thanks for your interesting presentation. And she was wondering about the last PhD topic on how is nature-based solutions taken into account in this port management program or studies.
Yes, so in this case, let's say the nature-based solutions that are looked at in this salty solution problem project, they are typically of quite a large scale nature, in the sense that they are the things we are looking at now are they are trying to influence, let's say, the hydrodynamics, right? So for example, the topic that Sebastian is now investigating in his MSc thesis, it's looking at, let's say, this shallowing of the inland waterway, right? So that's just by and then either by natural causes waiting for the sedimentation to have occurred, or actively changing the river profile. That could be a way that you could actually influence the way that the hydrodynamics interacts in the estuary. And there are other things that you can think of. So also in more open estuaries, you might think of interventions that influence the mixing, so that you have maybe less stratification, and thus maybe you influence the intrusion of the salt wedge into the estuary. But yeah, the whole point of this PhD is also that if you have a measure that actually influences the hydrodynamics, well, then you can almost be certain that it will also influence logistics, right? So it will create, let's say, harder to navigate situations, or maybe increasing tidal windows or something like that. So yeah, that's the kind of things we are thinking of.
Okay, thank you, Mark. Just one small request. Can you stop the presentation so we can see each other?
Yes, I can.
Yeah, I think it's better now. Yeah, thanks.
No, I agree.
No, thanks. We have another question here from Vincent Besson. He's a former colleague from us, but now living in the US. So, Vincent?
Yes. Well, first, thank you very much for the lecture. It was very interesting and a lot of things to think about. And maybe just before the specific question about the data, I mean, those models are really useful for a lot of decision making or policy making. And I think in Argentina, for now, the main challenge is to gather data and to gather data set and to bring those data and to be able to use open data, and yeah, this is a big challenge to start constructing those data sets to be able to use them again and again and for further investigation. And well, that's one thought about how building those models in Argentina. And the specific question was about the emission and consumption models you mentioned in the second PhD, I think. And my question was how, if it was possible to validate or calibrate those models using real-time or real-life data, and what kind of data you can use to validate those models and CO2
emissions
and so on. Yeah. How can you verify your findings?
Yeah. So that's of course a very good question, and I think so. The way we did that hasn't. That's always the case, but one of the things that we could use actually is let's say from recent investigations by our public works department, Rijkswaterstaat. They had interviews with different captains and asked them to share information with their estimates. So how big is your vessel? At what speed do you use roughly? How much fuel per hour, let's say? So we have what is, you could call it a little bit anecdotal information, right? So you don't know exactly all the details, but you know, ballpark estimates. And those ballpark estimates were actually quite, for the fuel use, were quite close. So sometimes we couldn't really match it because we actually not only need information about the water, about the vessel dimensions, but we also need to know in which section of the waterway it sailed. So if you just know, I have a vessel this big and I use so many fuel per 100 kilometers. Yeah, if you don't know which stretch it is and if it was with or against the current, it's really hard to verify, right? So, but okay, so we still thought that we could get quite close to this anecdotal information, and we are now really looking into much more detailed studies. The first thing that is now being done by an MSc student, he's looking at a dredging project. So that's not really like an inland shipping project, but a dredging project. And there the benefit is that all these dredging vessels, they really log in great detail all kinds of processes on board. So this will allow us to get a much better idea about how well we are able to estimate these energy usages. And one thing that makes it a little bit difficult for dredging projects is that you see that they have a very irregular use of power when it comes to sailing and stopping, right? So to get into motion, they use a lot more energy, but then once they are in motion, they can basically float for a long time to actually reach their final destination. So that part is maybe a bit more difficult. So we're still looking at ways to interact with, for example, pilots in the port of Rotterdam to see if we can get some onboard measurements so that we can verify it better. So this is definitely something that's high on our list to do.
Okay, thank you.
Okay.
Well, thank you, Mark. I think so far we do not have further comments, questions. I don't know, Raúl, if you would like to address some final words with Mark or discuss a few topics.
Just to say thank you to Professor Van Koningsveld for the excellent presentations. I think that he has given all the audience a lot of aspects to think about. So again, thank you very much, Mark. And we hope to see you in Buenos Aires soon.
I hope so too, of course. So that would be an excellent additional dimension to this whole interaction. And thank you for inviting me to give this presentation. It was my pleasure. And if there are any other questions that come up maybe later, then please feel free to send them afterwards so that I can still respond. And then, thank you for the opportunity to present.
No, thank you, Mark. Thank you for all your willingness and excellent attitude to share all the knowledge from TU Delft with us. It's highly valuable, not only for our cooperation between our universities, but for all the community within South America and within Piank. It's a pleasure.
Excellent, excellent. Well, it's my pleasure as well.
Well, thank you.
Okay.
We are talking soon.
Absolutely, yeah. So I'll attend tomorrow's lecture for Alex.
Exactly.
Yes.
Okay. Thank you for your attention, and I'll see you next time.
Okay. Bye.
Okay.
Thank you.
Okay.
Bye-bye.
Bye-bye.
Bye-bye. Cheers.